Hello everybody and welcome to the bonus episode. So we are going to be looking at how to basically do a paired sample t-test from scratch. And to prove that it's from scratch, I even left there's no data here, right? Because I wanted to make that up as we go along. But just so you can kind of see, I've already set up some things to save us a little bit of time as we do this. So the practice example that you see here is you suspect that people sleep better with a ceiling fan on than when the ceiling fan is off. You record the hours of sleep your participants get for one night under both conditions. You can assume an alpha value of 0.05. So this is another kind of twist on the paired samples t-tests. Here we're looking at this is a before and after, but it doesn't always really look like it. What we have here is essentially like condition 1 versus condition 2, which is totally fine, because the key thing here is that we are using the same participants. That's key. If we weren't using the same participants, we have to use a different test. Alright, so let's talk about what our numbers here are. I'm just going to be randomly kind of choosing some stuff. So I'm going to say 7, 8, 5, 6, 7, 8, 6, and 10. Alright, I said 10 and I wrote 9. Alright, so that's 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, and then with the fan off, I'm going to say 6 and 7 and 5 and 7 and 7 and 7 and 7 and let's go with 8. Alright, so let's see what happens here. Now, I did do one thing in mind, and it was, I'll show you why I was a little bit hesitant here, is because I wanted these to be kind of similar means. So well, never mind. We don't have to do that. We actually don't need to actually calculate the mean for this column. So what I want you to do is I want you to pause this video and try to work out these 6 steps. So the first 4 that we always do, and then these other additional 2. So go ahead and test yourself. See how good you are at this. Without my help, I believe in you. You can do it. Go ahead and pause this and give it a shot. Alright, so how did it go? Did it go okay for you? Let's walk through it step by step to show how it's done. The first step here is the hypothesis. What's the hypothesis? Well, I'm looking down at my practice example, and you can see that I mentioned that I suspect, so I predict that people sleep better with a ceiling fan on, which means that I suspect that this column is going to be better than or larger than this column over here. So I am actually going to put this in this kind of notation. So I'm going to have HO, I'm going to have HA, and I'm going to say for HA that the mean difference is going to be, which one do I want? I suspect that the mean difference is that it's going to be greater than 0. So why did I choose that? Because I think that this condition 1, is going to be bigger than condition 2. And so the change, once we subtract these, will probably be positive, which is why I have this expressed this way. For the null hypothesis, we're going to do the opposite, right? So we're going to be, the mean difference here is going to be less than or equal to 0. Alright. So that is pretty much it, I believe. Yeah. So we can phrase it that way. If you wanted to, you could even say, like, the mean for ceiling fan on is greater than the mean for ceiling fan 2, or without ceiling fan. And that would be perfectly fine from a statistics point of view. So there we go. Let's talk about the critical value. How do we find the critical value? I can assume an alpha of 0.05. The other thing that I need is going to be the degrees of freedom. How do I get that? So my degrees of freedom, I'm going to go ahead and put a little, I don't want to put it there. I'm going to put over off to the side, my degrees of freedom is going to be 1, 2, 3, 4, 5, 6, 7, 8, 8 minus 1, because it's n minus 1. And that's going to give us a degrees of freedom of 7. Alright, so let's find that calculator. I'm going to be putting in here that degrees of freedom is 7, got the significance level fine, and I'm coming up with, do I want the one-tailed test or the two-tailed test? For this one, I actually want the one-tailed test because I have a specific direction in mind whenever I talk about these things. So that's going to be my t-value. Now, it looks like positive 1.89. All right, so let's think about for just a moment what that distribution looks like. So this would be a difference of 0, and then what was it one more time? 1.89. Okay. So that means I'm going to be looking for something not super far down the tail of positive 1.89, and then down here will be negative 1.89. Although you don't need to do the negative aspect of this because our prediction is purely in the positive. So we are expecting something over here. All right, so let's do the magic here. Now, what do we do whenever we are, oh, sorry, my critical value. I can put this t crit. It's going to be equal to positive 1.89. All right. And, okay, yeah, so let's get into it then. So what's the next step? The next step, this is where things get so much different than one sample t-test. I'm just going to be basically subtracting these. And so I'm going to say that this is the difference. Oops. And so I am going to be subtracting from this way. And this is a little bit different than how I did in the chapter, but all that really matters is that you know which of these conditions is going to give you a positive value, and I know that this is the one that I suspect is going to give me a positive value. So I'm going to subtract across this way. If you're working with time point 2 versus time point 8, it might be a little bit different, and depending on how you phrase your hypothesis, just make sure that you're keeping track of those things. So the difference here, 7 minus 6 is going to be 1, 8 minus 7 is going to be 1, 5 minus 1 is going to be 1, 6 minus 7 is going to be negative 1. Wait, yep, negative 1. 7 minus 7 is going to be 0. 8 minus 7 is going to be 1. 6 minus 7 is going to be negative 1. And 9 minus 8 is going to be 1. I'm missing something here, aren't I? You're probably screaming it at me. Did I? This should be 0. Why 5 minus 5 should be 0? What was I thinking? Is this right? So 7 minus 6 is 1, 1. 0, 6, 7 is negative 1, 7, 0, 8 is 1, negative 1, 1. And so if I add these up, that's not giving me, if I had the right number of values, 1, 2, 3, 4, 5, 6, 7, 8. Oh, I'm sitting here and I'm racking my brain. I'm like, why is it not equaling to 0? You don't have to. That's my bad. This does not need to necessarily equal to 0. I don't know what I was thinking. My bad. I had a brain fart. And so this does not need to equal 0, but the next step should. So what is the next step? The next step is that we're going to get our mean difference, right? So we're going to get our mean difference. We'll find that in a moment. And then we're going to be subtracting that mean difference to get our residuals of the difference. That's where we're going to be adding those up to get to 0. So let's find out what the mean difference is. So I've got 1 plus 0 plus negative 1 plus 0 plus 1 plus negative 1 plus 1. And that gave me a format error because I typed it in incorrectly. Sorry, y'all. 1 plus 0 plus negative 1 plus 0 plus 1 plus negative 1 plus 1. I'm getting 2, which sounds right to me. So that's 2, and then I'm going to be dividing that by 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 2 divided by 8 is going to give me 0.25. So my mean difference is going to be 0.25. In other words, the average difference that people have when they have the fan on versus when they have the fan off is about a quarter an hour of sleep. People get more sleep when they have the fan on compared to a fan off. But we need to make sure that's statistically significant. So let's go through all the hurdles here. Where now that we have this column right here, we can think of this as like our X column. We're going to be doing all the same steps we've done so far this semester. So I'm going to be taking 1. I'm not going to be subtracting that by 0.25. This is going to give me 0.75. This is going to give me negative 0.25. This is going to give me negative 1.25. This is going to give me negative 0.25. This is going to give me negative 1.25. And this is going to give me 0.75. Alright, so now these should add up to 0. So let me do that. Ooh, I'm not getting this right. 1, 2, 3, 4, 5, 6. Okay, I'm missing a number. Oh my gosh. Okay, I see which one I'm missing. I'm missing this one, I believe. Sorry, y'all. Sorry. This is what I get for writing it out on a tablet, not trying it on a sheet of paper. So this is that. This should be negative 0.25. Then the next one is a 1. I think this is the one that I skipped earlier. You probably saw it and was yelling at me through the computer. That should be 0.75. This is going to be negative 1.25. And this is going to be 0.75. That should give us 0. But I'm just going to double check. So I'm adding all this together. Okay, it does. Yep, gives me 0. Just making sure. That means I'm on the right track, and you can see why it's so important now to add these things up, because I would have totally missed a number and then been working with 7 numbers instead of 8. Alright, so it's our residuals. Now here comes the fun part, because we're going to be taking each of those and we're going to be squaring them. Alright, so we're going to be squaring each of those. So it's going to give us some really gnarly, nasty numbers. Alright, so this first one right here is going to be equal to 0.56, and I have a couple of these, so I'm just going to fill those in. And then I'm going to be doing 0.25 squared, and that gives me an even smaller number, 0.06, and I have that on 2 separate occasions. And then I got negative 1.25 squared is going to give me 1.56, and also for right here 1.56. And I think I missed this 0.75, so it's going to be 0.56. Let me count. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Alright, now I'm going to add all those up. That wasn't as bad as I thought it was going to be. I thought it was going to be really bad. Alright, so I am getting this number right here, 5.48. Alright, so 5.48, that's our sum of squares. And we can put that now into our standard deviation formula. So this is going to be the standard deviation of the difference, which is the exact same formula. So we're going to be looking at essentially the sum of squares up here, which is going to be, it's going to be basically x times 0.1 minus 2. Basically, what I'm trying to say is it's going to give you your sum of squares. It's going to be 5.48 divided by n minus 1, where n minus 1 is going to be 8 minus 1, so it's going to give me 7. And we can rock and roll. We're ready to go from here. So I'm going to be dividing 5.48 by 7, and that is going to give me this. I'm going to get the square root of 0.78, which is going to be equal to 0.88. So our standard deviation is 0.88, and we are almost done with this third step, which just takes forever. So now we are going to get, I'm going to get the sampling, error. The way that I'm going to do that is going to be 0.88 divided by the square root of n, and the square root of n is going to be the square root of 8, and that's going to, what is the square root of 8? .83, and now I'm ready to divide these, and that gives me 0.31. Alright, so 0.31 is my sampling error. So now I'm ready to plug in the values that I need here, and that is going to be, my t is going to be equal to the difference of the sample subtracted by the hypothesized difference divided by the sampling error. We have all those ingredients. Let's put them into the stew. It's going to give me, the mean difference is going to be, is up here, 0.25. The hypothesized difference, which is 0, divided by the square root of the sampling error, basically, which is going to be 0.31, excuse me, 0.25 over 0.31, which is going to be equal to what? 0.25 divided by 0.31, it's going to be equal to 0.81. And so I'm going to come over here now, finally. Now I'm going to say it's going to be 0.81. Alright, so awesome, that felt good, but unfortunately when it's time to make a decision, I'm looking over here, my 0.81 is going to fall somewhere like right here. And that is not in the rejection region, my friends. We cannot reject the null because we did not pass that. So we're going to say we failed to reject the null. Alright, we've got a couple of more things now, which include effect size. So I'm going to erase some of the stuff up here, just so I can have a little bit of extra room. Actually, I'm going to erase this down here. I'm going to try to squeeze this all in, into one frame here, just so that way you can see it all together at the end. So I'm just erasing the distribution now that we've already rejected, failed to reject the null. Excuse me. And Cohen's d is going to be equal to the difference subtracted by the difference divided by s, and it's s, not sampling error, which means that d is going to be equal to 0.25 subtracted by 0 divided by s, which in this case is, what was it, 0.88. And that is going to be equal to 0.25 divided by 0.88. 0.28. So that's actually better than I thought it was going to be honest with you. Which, so basically what that means is, if this was a statistically significant effect, then what we would say is 0.28. Sorry, one second, let me get some coffee. That the difference between having the fan on versus the fan off is roughly about 1/4 of a standard deviation away from one another, which is that's a pretty low effect size, but it's a meaningful one. Alright, and then finally we're going to do the confidence intervals. Now confidence intervals, as I mentioned before, are not really all that easy to do they're not appropriate really whenever you are looking at a confidence interval and you have a one-tailed hypothesis. But we're going to roll with it because we want the practice. We're going to be basically putting in all of the usual ingredients. So if you don't remember, the confidence interval is going to be equal to that mean difference plus or minus the t critical multiplied by the standard deviation divided by the square root of n. And that gives you your 95% confidence interval, because we're using the t critical value from the 95, from the alpha value of 0.05. So if I plug these in here, that's going to give me 0.25 plus or minus t crit, which is 1.89, multiplied by this over here, which is just our sampling error, 0.31. And then we are going to multiply those together. That's going to give us our margin of error. So 1.89 multiplied by 0.31 is going to give me 0.59 when I round up, plus or minus 0.25. And once I add those together, then that's going to give me my confidence interval for 95%. So it's going to be 0.25 plus 0.59. It's going to give me my upper bound, so it's going to be 0.84. And then my lower bound is going to be 0.25 subtracted by 0.59, and that's going to be negative 0.34. So, how do we interpret this? Basically, and I should write over here, the effect size for this, for D, is going to be equal to 0.28, and for the confidence interval, that is going to be negative 0.34 and 0.84, and we are done, y'all. So what does this mean? How to interpret this? Basically, if you see the number 0 and it falls inside this interval, then you cannot reject the null. If it falls outside of this interval, like if it falls down over, below it or above it, then you can reject the null. Because what we're saying is that we're 95% confident that the actual population difference between these two comes between these estimates. And so it could possibly be 0, right? So our null hypothesis was that it is equal to 0 or greater than or less than the mean would be less than 0 or equal to it. And that is what we see here, that 0 falls in here, so we can't reject the null. And that just backs up what we found when we compared the t critical to the t obtained, because remember, the 95% confidence interval is just another way of doing hypothesis testing, but just kind of another way to kind of illustrate that and to express it. And that's pretty much it. So, I know this video took a while, but this was a lot of work, and, and partly I was kind of narrating everything, which I know can slow things down. But I know how much work this stuff can be. That's usually why I try not to assign numbers this gnarly. It's because they're hard to calculate and take forever. But if you have any questions while you're working on this, let me know. Or if I screwed up somewhere, God forbid, let me know that too. I hope you have a great day, and let me know if you have any questions. I'll see you later.